Buenos días a todos. Les damos la bienvenida a esta séptima sesión del seminario temático COVID-19 que estamos realizando desde el Centro Multidisciplinario de Modelación Matemática y Computacional de la UAP, el CEMAC. Y en el día de hoy, en esta ocasión, la conferencia será impartida por el doctor Vitaly Volpert, que es profesor de la Universidad de Lyon 1, y la conferencia tratará sobre la modelación del comportamiento de la pandemia, considerando hipótesis de heterogeneidad de la población. We also welcome Professor Volpert and his collaborators. We appreciate so much his participation in our seminar today. As we always do, next we will make a summary of the professor's academic career. Professor Vitaly Volpert is a senior researcher at the National Center for Scientific Research, CNRS, in France, and director of the Interdisciplinary Research Center Mathematical Modeling in Biomedicine at the People's Friendship University of Russia. He got his PhD at the Institute of Chemical Physics of the USSR Academy of Sciences and habilitation at the University Lyon 1. His scientific interests include partial differential equations and their applications to mathematical modeling. He is an author of about 400 scientific publications, including 4 monographs. So, Professor Volpert, you can start now. Thank you very much.
Thank you very much for the invitation to participate in this conference, this cycle of seminars, and also for this introduction. I share my screen. Here it is. And so yes, today we will discuss this question about epidemic progression in a heterogeneous population. And this is a joint work together with my colleagues from India, Malay, Banerjee, and Samiran Ghosh from the Institut, Indian Institute of Technology in Kanpur. And as it was announced, it says this presentation, it's a part of the cycle of conferences announced here. And also there will be this book with several chapters, and we participate in this book with a chapter with a similar title about epidemic progression in a distributed heterogeneous population. But in my today's talk, I would like to present it. It's a little bit broader point of view, and I will also present in the beginning several other questions on which we work on. And in fact, all that concerns what we call multi-scale problems. And here in the slide, you see from virus to population. So what seems to me very interesting and very amazing, if we take all virus particles from all people around the world infected with this coronavirus, we can put all these viral particles just in one glass. So it's really like very different scales, just one glass with all these many virus particles. You see, it's about 10 to the power 17. The whole Earth, all countries suffer from this epidemic. So how to study this problem, how to model this problem with such different scales. And here in the slide, I show, like in a schematic way, different questions which we have here, including, in particular, infection spreading in cell culture. You see here at the left. Of course, immune response, and it includes innate and adaptive immune response and other questions related to inflammation. Very important also, of course, virus mutation, evolution, competition. All that, these 3 different topics come together in this, what is written here. At the bottom, infection development in the human organism and tissues and organs. And on the other hand, we have all these questions related to epidemiology, and these epidemiological questions, they come together with these other questions in what we call immunoepidemiology. And of course, today I cannot discuss all these questions. They are very interesting, but they are very complex, and it's a very wide area of research. But in the beginning of my presentation, very shortly, I will discuss the several questions related to the immune response, just to show what is happening now in mathematical modeling related to this coronavirus epidemic. And then the most part of my talk, I will discuss these questions related to epidemiology. So starting with infection development of cell culture, this if we take this coronavirus and the culture of epithelial cells, there are experiments like that. And we can see here in the left image, these are cells, and these red spots, these are cells which are infected by virus, and then virus is produced by these infected cells. It goes into the extracellular space, it infects neighboring cells, and like that, this viral infection propagates in cell culture. And if we measure experimentally total virus concentration in the whole cell culture, it will be something as shown here in these curves in the right image, that here the horizontal axis is time, the vertical axis is total virus concentration, and these curves show how this virus concentration evolves in time. And there's something very interesting in these curves, and I will return a little bit later. But now I will show how we can model this development of viral infection in cell culture. And in fact, the simplest but rather appropriate mathematical model is shown here. It's three partial differential equations for the concentrations, for the concentration U of uninfected cells, the concentration I of infected cells, and the concentration V of virus. So what we see here in the first equation, so virus V contaminates uninfected cells U, and this is why the concentration of U decreases, the sign minus, but the same term enters here with the sign plus. It's how cells become infected, and at the same time, infected cells can die. This is why there's this term here, minus beta I. And the third equation for virus production and virus diffusion, so this is diffusion term, and the production term here, it's I, it's infected cells produce this virus, and this substrate tau means that there is time delay. So this is very important, that virus needs some time to begin to replicate. And also virus can die. So here we have this minus sigma v term. And then there are different ways to study this model. Of course, numerical simulations, there are some analytical methods. And here in the middle image, you see numerical results, how this infection propagates in cell culture with this brown curve, it's virus concentration, green curve, it's the concentration of infected cells, and blue curve, the concentration of uninfected cells. And then, similar to the experiments, we can find the total virus concentration in cell culture as a function of time, what we see here. So in these graphs, the horizontal axis is time, and the vertical axis is this integral of this virus distribution. It's the total virus concentration as a function of time. And now we can compare these experimental results shown with red dots and numerical results shown with this blue curve here. And we see that this model describes quite well the experimental results. And here, looking at these experimental results and this modeling results, we can identify three stages of the development of viral infection in cell culture. In the beginning, you see that total virus concentration decreases here. Why it is so? Because, as I mentioned before, virus needs some time to begin to reproduce in infected cells. Here, it's about 2 hours. For some other viruses and some other cell cultures, it can be, for example, up to 10 hours. And then when virus begin to reproduce in the infected cells, its concentration rapidly grows, such an explosive way, reaches its maximum, and then it's the second stage. And then the third stage, its concentration remains either more or less constant, as in the left graph, or it grows slowly, as in the right graph. And this last stage corresponds to the propagation, like shown here in the bottom figure. You see these virus concentrations in different moments of time with this like peak-like or pulse-like distribution, which moves from the left to the right, and the total virus concentration remains approximately constant. And this is what we called in mathematical modeling a reaction diffusion waves. So with this modeling and these experiments, we can obtain a rather good description of infection spreading in cell culture, in particular for the coronavirus. And then the next step in the study of these questions is related to the immune response. Of course, if we want to study infection progression in the human organism, then we need to consider the immune response. And the immune response, it's a extremely complex system which consists in several parts, and in particular innate immune response. In this diagram, it's the upper part, and this innate immune response, it includes in particular interferon production by the infected cells, sorry, and also cells of innate immune response such as macrophages and dendritic cells. And then the cells of innate immune response, they initiate adaptive immune response with T lymphocytes, B lymphocytes, and in particular cytotoxic T lymphocytes, they eliminate infected cells, and B lymphocytes, they produce antibodies which eliminate free viral particles. Of course, there are many other things related to that. All that is accompanied by inflammation of the infected tissue, and in particular, excessive inflammation can lead to the cytokine storm, which was widely discussed during this epidemic. And then we can model all that with, in particular, what is shown here with ordinary differential equations or with more completely complex partial differential equations. Of course, I will not stop on these results and on these models in detail. I would like also only to mention now that these models allow us to study the incubation period of the disease, also the maximal viral load, how the disease progression depends on the initial viral load, how it depends on the individual immune response, and also we can study vaccination. The next step in modeling of this coronavirus disease is related to some tissues of our organisms which are mostly concerned, in particular in the lungs. And here there are basically two parts of the lungs are concerned. These are bronchi, with shown here in the upper top figure. And what is very important here is that there are so-called goblet cells and cilia cells, and the cilia cells, they possess this what is called cilia. The cilia oscillates and they push this mucus layer you see at the top of this figure. Mucus is a viscous fluid, and it plays a very important role in our physiology. It moves along the epithelial tissue, and it helps us to remove all this like bacteria, viruses, and other things from the lungs. But if the infection, in particular coronavirus infection, develops here, it concerns this cilia cells and concerns also goblet cells which produce mucus. And so mucus can become more viscous. It doesn't move in the same efficient way, and inflammation. There is a positive feedback between mucus motion and inflammation. Mucus can accumulate here, and it can result in important respiratory problems. On the other hand, this coronavirus infection can concern this alveoli, and it can lead to blood coagulation in small blood vessels in the lungs, and this is one of the main causes of mortality during the coronavirus disease. So this is explained a little bit more in detail here. I will not stop on that in detail. You see the cilia cells and mucus motion here, and virus infect the cells and just damages the tissue, and it cannot function in a normal, efficient way. And concerning alveoli and small blood vessels, it is shown here. And we studied this question before with some other types of inflammation, and we observe here with this modeling how inflammation leads to spontaneous blood coagulation and to the occlusion of blood vessels. So this I very briefly presented the several questions related to the infection development in cell culture and in the human organism. And then I will pass to the main topic of my today's presentation, to the epidemiological models. And then very briefly at the end, everything will come together, this epidemiological models and this infection development and immune response. But very briefly, I will discuss these immunoepidemiological models. So let us continue with the epidemiological models. Of course, we should be aware that the problem is quite old. In fact, the first epidemiological models were developed by Bernoulli, D'Alembert, Laplace, and in fact, all these questions are studied already for a long time, beginning from the 18th century. And one of the mostly well-known and widely used model is so-called SIR model, susceptible, infected, recovered, shown here. It contains three ordinary differential equations for three classes of population: susceptible population, infected population, and recovered population. And infected population I, it infects the susceptible population. So this is why we have here minus KIS, and the same term with the same sign plus enters here for the infected individuals. And then infected individuals can recover with the rate beta I, which we show here, or they can die with the rate sigma I. So this is the classical model, very well studied, of course. And here in the right image, we see typical behavioral solution of this ordinary differential system of equations. With this yellow curve here shows the total density of the susceptible population. It decreases in time. Infected population, it increases in time. Recovered population, blue curve, increases in time. And infected population, it's a red curve. First it increases, goes through the maximum, and then decreases. And then what is very important in this model, that it allows us to introduce what is called the basic reproduction number. This is a parameter which is shown here, which is expressed through the parameters of this model. And if this basic reproduction number is less than 1, then the epidemic does not develop. The total number of infected individuals decrease. But if this parameter is larger than 1, then the epidemic develops and the number of infected individuals grow. Then, if we consider the epidemiological data for this COVID-19 epidemic, so what is shown here, two graphs, and of course, everybody knows them, and we observe the evolution of epidemic. So what is shown here, it's daily new cases in the left graph for the whole world population, and in the right graph, it's daily deaths also for the whole world. And what we see here that from the very beginning of the epidemic, how this curve changes in time, for example, for the daily cases. And in fact, behavior of these curves is completely different in comparison with what we have here in this classical SIR model. And then if you take also not the whole world data, but data for some countries, for example, in Mexico, in the top left figure, here in France, top right, and also in Russia or in India, in other countries. So what is we can remark right away that these curves are in fact very different. And the second observation, as before, that they do not correspond at all to this SIR or to other epidemiological models. And of course, we understand very well why it is so, because in fact, what happens here is that the coronavirus disease is in some sense quite different from the epidemiological point of view in comparison, for example, with the seasonal influenza. And this difference or specific features, the main of them is, first of all, it's a rather high mortality rate. It's about 2%. And because of this high mortality rate, we cannot expect to have collective immunity. And even now, almost 1.5 years after the beginning of epidemic, the collective immunity is not reached, far from that. And this is, of course, very different with the seasonal influenza, where collective immunity is reached about 2 months after the beginning of epidemic. So since we cannot count on collective immunity, so there are some other measures that should be adopted. And the main measures from the very beginning, it became clear that it should be social distancing, lockdown, quarantine, various sanitary measures. So the which we observe here, in fact, this is that, as I mentioned before, they are not described by these classical epidemiological models because they don't describe the what we can say the normal, in some sense, development of the epidemic, but all these curves are the results of the measures of social distancing, where the coefficient beta, the coefficient of interaction between the individuals and the populations, are controlled by the measures of social distancing. And also what was noticed from the very beginning of this epidemic is that the heterogeneity of the population can also play a very important role. And this heterogeneity concerns different questions. In particular, there are different subpopulations with respect to the disease transmission and heterogeneity in space between different countries or between different regions in the same countries. Also, the heterogeneity in the individual immune response. In my today's presentation, I will basically discuss this question, this heterogeneity of the population with respect to these different properties. So let us now consider probably the simplest model of a heterogeneous population, where we have two subclasses of susceptible, S1 and S2. It is different with the previous SIR model, where there is only one class of the susceptible population. And what is the main difference here? It is in fact that this subclass S1, it can be infected by I1 or it can be infected by I2. And similarly, for the class susceptible class S2. So it can be infected by these infected individuals from these two different subclasses. And what is the difference between them is that this coefficient of disease transmission, beta 1, 1, and so on, these coefficients can differ between each other. So this means that these two subclasses of susceptible population and also infected population, they differ from each other by the rate of disease transmission. And we will see a little bit later that this is very important, and this can change completely the progression of epidemic. But if we begin with numerical simulations, just to see the behavior of these populations. So an example is shown here. There are two figures. In the left figure, it's the first subpopulation, S1, and in the second figure, the population S2. And here, the first subpopulation S1, it's the subpopulation with high disease transmission, and the population S2 with low disease transmission. Why there is this difference? For example, it can be because of some professional or social activities. Individuals from this population have more interactions than the individuals from the second population. So the rate of disease transmission here in the first subpopulation is higher than in the second subpopulation, or in the other words, the coefficient beta 1, 1 is larger than the coefficient beta 2, 2, and respectively, these cross coefficients beta 1, 2 and beta 2, 1 also change. So, but what we see here, we have here several different curves, and each curve corresponds to one particular relation between two classes. For example, if we take this violet curve, this means that initially from 10 million population, 3 million belong to the first class and 7 million to the second class. And then for the yellow curve, this proportion is changed, and so on for the red curve and for the blue curve. So we consider different relations between different proportions between these two classes of populations. And what we see here, and it's very interesting from my point of view and an unexpected result, is that for these different proportions between these two classes, if we consider the first subpopulation with high disease transmission, at the end for large time, so the horizontal axis is time here, and the vertical axis it's this population. So at the end for large time, this S1 population converges more or less, not exactly, but almost to the same value. This, I think, it's important to understand what happens here, because at the same time, for the second subpopulation with low disease transmission, these limiting values, what is also called final value of epidemic, so these values are completely different. So in fact, this first subpopulation with high disease transmission, in some sense, they are drivers of the epidemic. They are drivers of the epidemic, and when their number becomes sufficiently small, then the epidemic stops. So in some sense, we can say here that there is collective immunity reached by the first population, and this is sufficient to stop the epidemic. But for the second population, this final number of susceptible individuals, as you see here in this graph, can be really very, very different. So this is the first important conclusion, that in the heterogeneous population, the epidemic progression can be very different, and it is basically driven by this first subpopulation with high disease transmission. I will return to this question later, but first of all, as before, similar to the homogeneous population, we can find the basic reproduction number. So now it depends, of course, on the proportion between these two different populations. It is called K. So N here is the total population, S1 is the first population, so K is the S1 over N, and then we have S2 over N is 1 minus K, and the basic reproduction number, it can be easily found analytically. It depends on this parameter K. Then if we assume that both subpopulations have the same coefficients beta, the same disease transmission, then we return back to the homogeneous population. It's just a particular case, but we are mostly interested, of course, when these coefficients are different. And then we can find this final value of epidemic, the values of this first susceptible population and second susceptible population for large time. These limiting values we can also find analytically, well, more or less similar as for the homogeneous population, except for that it's not just an analytical expression, but it's a solution of this algebraic system of equations. So we can find analytically, first I showed numerically, but we can also find analytically this final size of epidemic. And this means that the susceptible populations, the limiting values for large time. So what we can do here, we can find the basic reproduction number, which determines the epidemic progression, whether it progresses or not, and we can find the final size of epidemic, both analytically and numerically. But what is when we analyze this data, another important conclusion which we can make is that, in fact, basic reproduction number does not determine the final size of epidemic. This is also, I think, important to understand, because well, the epidemic started, there were a huge amount of work. We have this exponential growth of the infected population. With this exponential growth, we find the basic reproduction number and what? So the purpose of this modeling is to predict further epidemic progression. But in fact, we cannot, and this I will explain, we cannot predict the epidemic progression in the case of a heterogeneous population if we have only basic reproduction number. And one example is shown here. So we have several parameters in the model, and we can choose these parameters in such a way that for different values of parameters, we have exactly the same basic reproduction number. So I repeat, we have the same basic reproduction number, but we change this coefficient beta 1, which shows the rate of disease transmission in the first subpopulation. So again, for different values of beta 1, and for different values of K, it's a proportion between two populations, we have exactly the same basic reproduction number. And what we observe here, the final size of epidemic is completely different. So for the same basic reproduction number, we obtain very different final size of epidemic, meaning the limiting value of susceptible population. So in the blue curve, this is final size of the first subpopulation. In the red curve, it's final size for the second subpopulation, and yellow curve shows its sum for the total population. So we see in this graph exactly for the same exactly basic reproduction number, the final size of epidemic can change several times. So the conclusion is that this basic reproduction number, so which we determine from this exponential growth in the beginning of epidemic, this is not sufficient to predict further epidemic evolution. So we continue to study this model, and what we can determine next is the maximal number of infected individuals. Of course, this is very important because in particular, when we discuss available beds in hospital, things like that, we need to estimate how many infected individuals we can have. And you see here again, I present this graph for the homogeneous population. This red curve, the number of infected individuals, it has a maximum, it goes to the maximum, then it decreases. So what is the maximum, in fact? How we can determine the maximum? And again, for the homogeneous population, we can determine it analytically. And if you consider a heterogeneous population, we do some approximation. So it's not exact analytical result, it's an approximate analytical result, but we can determine also the maximal number of infected individuals for the first subpopulation, for the second subpopulation. Here we see the comparison of the numerical result. It's a solid curve, and this approximate analytical result, it's dashed curve, and they are very close to each other. So we can obtain analytically quite good approximation of numerical results. But again, what I want to show here is that for the same basic reproduction number, but for different coefficients beta 1, 1, so we can obtain absolutely different values in the number of infected individuals, maximal number of infected individuals for the first subpopulation, for the second subpopulation. Especially we see this difference for this second subpopulation. It can change several times, and of course this is very important from the point of view of the evaluation of hospitals and available beds. So the next question which we study is vaccination. So how we can model vaccination in these epidemiological models? In fact, if we say that we apply vaccination at some moment of time t0, then we decrease the number of susceptible individuals. So we see here that this number is decreased. So V here is the number of vaccinated individuals in the first subpopulation, in the second subpopulation, and the proportion between them. So if the total number of vaccinated individuals is V, so then we have here kappa V for the first subpopulation, the number of vaccinated individuals, and in the second subpopulation, it is 1 minus kappa V. And again, as before, we apply this vaccination, and we see that the result is very different depending whether we vaccinate the first subpopulation or the second subpopulation. So when we vaccinate only the second subpopulation, and the second subpopulation is a subpopulation with low disease transmission, it's a red curve, and the first subpopulation with high disease transmission, it's this blue curve. For the same number, for example, we take here 0.06, and this means that only 6% of the total population is vaccinated, and then either we apply the 6% to the second subpopulation or to the first subpopulation. If we apply it to the second subpopulation, the influence of vaccination is small. We just subtract the same 6%. So what this means, if we apply vaccination to this low disease transmission subpopulation, yes, we protect some people because we vaccinate them, but we don't stop the epidemic. But if we apply this vaccination, the same, for example, 6% to the first subpopulation, and this subpopulation, which is a driving force of epidemic, so the result is completely different. We see that this curve is strongly decreasing, meaning that the result of vaccination is much stronger in this case for the total number of infected individuals, and also even more for the maximal number of infected individuals. We see that we can really strongly decrease the number of infected individuals if we apply vaccination to this first subpopulation with high disease transmission. I continue with vaccination, and we can also determine here how many vaccination doses we need to stop the epidemic, as shown here in the left graph, for different values of K. I recall that K is the proportion between different subpopulations. And then it's a complex graph which shows this V1 axis, V2 axis. It's how many doses we apply to the first subpopulation, to the second subpopulation, and how many doses we need to stop the epidemic. So this dark green area here, it's where the epidemic continues. But if the number of doses is sufficiently high, it's beyond this straight line, then we stop the epidemic by the vaccination. And these three different colors, green, red, and blue, they correspond to these different values of the parameter K, the proportion between subpopulations. This result in the left is shown for one single vaccination, but in fact, of course, this is not very realistic. Vaccination is extended in time, and here in this right graph, we show different vaccination strategies, where in fact it's not a single vaccination, but here it's 5 consecutive vaccinations with the same doses. And again, these vaccinations can be applied to the first subpopulation, to the second subpopulation, and we consider here different vaccination strategies. Each curve corresponds to one vaccination strategy. Vaccination strategy, this means the proportion of the number of vaccinated individuals between the first and the second population. Well, I will not discuss it in detail now, but the result is basically the same, that it is much more efficient to vaccinate the first subpopulation where the disease transmission rate is higher. Of course, there are other questions which I don't discuss here because some groups of population can be more vulnerable than other groups, and the role of vaccination can be not only to stop epidemic, but also to protect these vulnerable people. So the different vaccination strategy can take into account these different objectives of vaccination. Well, and we continue to study these model problems with two subpopulations. And the last question, which I will briefly discuss now here, it is about reinfection. So at the latest stage of epidemic, already even now, some people after some time, some recovered after some time, can become susceptible again. And in this case, we see here in the equations for recovered individuals, we have this additional term minus B1R1 minus B2R2. It's recovered individuals, they become susceptible again. We see here the same terms with plus here in the equations for susceptible. So then this means that there is this turnover between recovered and susceptible. And in this case, situation is different. So in fact, we have this transient period, the beginning of epidemic, which we can call the acute stage of epidemic. But then after some time, when this turnover between recovered and susceptible becomes important, so there is a new stage of epidemic, which we can call chronic stage of epidemic, where the number of susceptible and the number of infected, they converge to some stationary value, this endemic value of the epidemic, which is different in comparison with the acute stage of epidemic. And in fact, we can expect that after some time, after this vaccination campaign, which continues now, we can expect that the acute stage of epidemic will be finished, but it is also possible that we will enter into this new stage of epidemic with a more or less constant and persistent number of infected individuals. So I finish with this part of my presentation, and the conclusions which we can make for this model problem, which we discussed before, is that basic reproduction number in the heterogeneous population is not sufficient to describe the epidemic progression. Final size of epidemic, maximal number of infected individuals, the outcome of vaccination, all this strongly depends on the structure of the population. In this particular case, it's a proportion between the subpopulations with high and with low disease transmission. And finally, reinfection. So we can observe transition from acute to chronic stages of epidemic. Well, we started this model problem, and then we can consider more complete and more realistic models already more adapted for this COVID-19 epidemic, also largely discussed in the literature, so I will not stop on them in detail. But what is important here is that, again, we have these two classes of susceptible populations. Then we have infected individuals and infectious individuals. So infected, they already have infection, have virus, but they don't yet contaminate the others. After some time, they become infectious. Here, then there are several possible cases. These infectious individuals can become asymptomatic or symptomatic, as shown here. We suppose that asymptomatic disease progression is usually not very severe, and we can expect that asymptomatic individuals recover. But in the case of symptomatic individuals, again, the infected individual can either be isolated in quarantine, or if the disease progression is severe, can go to hospital, and from here, either this patient recovers or he dies. So this is a already more complete model, quite realistic for this COVID-19 epidemic. And then we can introduce these OGE models describing all these different subclasses. Well, of course, when we study epidemiological models, a very important question is about the values of parameters. And it appears that most of the parameters can be determined, because all these transitions, in fact, after some time during this epidemic, we know already this transitions rate between different subclasses, infected, infectious, and so on. So we know how much time each stage takes, so that we know the rates of all these transitions. But what we don't know these coefficients beta 1, 1, and so on, which characterize disease transmission from infectious individuals to susceptible individuals. So in these tables, we know the most part of parameters, but in fact, we don't know the most important parameters, and these most important parameters, beta, I, and J, which characterize disease transmission to susceptible individuals. So one of the important questions is how to determine parameters, and this is what I'm going to discuss briefly now. In fact, the approach we use in this works is that we use the data, available data before lockdown, during lockdown, and after lockdown. And our approach is that we suppose that before lockdown, the population is in fact homogeneous, because the measures of social distancing is not yet imposed, and the population behaves as a homogeneous population with the same transmission rate beta 1, 1 for the whole population. But then if we take the second period of time during lockdown, again, we have, we suppose, of course, it's an assumption, and an approximation. We suppose that everybody respects the measures of social distancing. So again, as before, we have homogeneous population, and from this curve, we determine now the second coefficient, beta 2. So what we have here in the first, before lockdown, we determine beta 1. During lockdown, we determine beta 2 by fitting the data. The cross coefficients beta 1, 2 and beta 2, 1, it's half sums of these two coefficients. So like that, using the data before and during lockdown, we determine all these coefficients of disease transmission. So after that, once we determined all these parameters, after lockdown, it remains only one free parameter, is K, is a proportion between two populations. So let us summarize. Before lockdown, we have homogeneous population, and we determine beta 1. During lockdown, we have homogeneous population, and we determine beta 2. After lockdown, we have a heterogeneous population. We have already determined beta 1, beta 2. They remain the same as before, but we have now two subpopulations, and the proportion between these two subpopulations is determined by this parameter K, which in this particular case, after lockdown, if we have already data, we can find, so we have only one unknown parameter is K, we can find this parameter fitting the data, or we can predict and estimate the value of this parameter for future development. For example, here, this parameter K after lockdown, in fact, this data was taken for Germany in 2020, and the value of parameter K during the summer of 2020, which is shown here, we estimate this parameter as 0.1, and in fact, this modeling was done exactly during this summertime, but we predicted that when the vacation is over, then this parameter can increase, and we took here a small increase from 0.1 to 0.15, and we see a very strong change in the behavior, a very strong change in the epidemic progression, and in fact, this is exactly what was observed in the autumn of 2020, not only in Germany, but in different countries, and this approach gave us a good approximation and a good prediction. But then this parameter can be used to control and to, in fact, suggest a strategy of the measures of social distancing and lockdowns. So we have just one parameter, and we can estimate now the values of parameters of this parameter from the previous data. So to conclude about this more complete models and parameter estimation, so if the heterogeneous population consists of two subpopulations, then these parameters of disease transmission can be estimated from the epidemic curves before and during lockdown, and then the parameter K, which characterizes a proportion of different subpopulations, can be used as control parameter, and it can be used to characterize the epidemic growth. But what is important to recall here, that this parameter estimation is possible because we consider only two subpopulations. If we consider more subpopulations, for example, there are many works now in the literature where they consider many different age groups. It can be 10 or 15 age groups. Then it is necessary to consider this complex contact matrices with many entries, with many elements, and it is very difficult, maybe even impossible, to give a precise estimation. So we consider that these models with two subpopulations, it's a good compromise between complexity and simplicity. We cannot completely ignore the heterogeneity of the population. So we take two subpopulations. If we take more subpopulations, we will have the problem of parameter determination. So again, to summarize, we think that two subpopulation, of course, it's an approximation, but it's a good compromise which allows us to give a rather good description of epidemic progression. Then very shortly about spatial heterogeneity. So before, in this previous part, we discussed this heterogeneity with respect to the rate of disease transmission. But then if we have this, what is called multi-patch models, so populations are distributed in space. It can be different countries, different states. So basically, the ideas are the same, but the models become more complex. And what is also important here, how these different patches interact with each other. So there are already another characterizations, this topology or geometry of this interaction between different patches, which should be taken into account. But similar analysis can also be done with basic reproduction number, final size of epidemic, and other parameters. And then we try to apply this approach to the epidemic progression in India, not in the whole country, but in 7 states around the state here, Maharashtra. Why here? Because this state was mostly concerned by the epidemic, at least in the previous first wave. So we consider this state and all these 6 neighboring states around it. And we see that disease progression is quite different in these different states. So the question we asked was how the interaction between the states, the migration of population between the states, how it influences the epidemic progression in different states. And one example is shown here. This is modeling of this data for these states. And then we considered how migration between states, how it influences the epidemic progression. And one example is shown here. And we see that this influence of migration between different states can be rather important for the epidemic progression. So we considered this group of questions related to the epidemiological models. And in the end of my presentation, I will very briefly discuss this immunoepidemiological models, where in fact everything here comes together: epidemiology and immune response and infection progression. And this is also related to the heterogeneity of the population, but in this case, with respect to the individual response. And why this question is important? Because we see here in this example, this is an example for the seasonal influenza. And what we can observe in this data, and in fact, here it's only one example, but it is similar for other data for seasonal epidemic, that we can observe here different stages of epidemic progression. Here, this maximum corresponds to collective immunity, and then the epidemic decays. But if we take only this growing part, if we take this growing part, then in fact, we can observe that there are different stages of growth. And again, it does not correspond at all to the classical epidemiological models. In fact, if we analyze more precisely these growth curves here in the right graph, so we see here this red curve, it's the first stage of epidemic progression, and then we continue, it's an exponential growth as it should be, but this exponential growth, this red curve, it continues here, but in reality, beginning from this point, we don't have this red curve anymore. We have a blue curve. And this blue curve is another exponentially growing function, but the exponent is different. And this is very important. And the same is shown here in the right graph in the logarithmic coordinates. So this in the logarithmic coordinates, it becomes just a linear dependence here, red curve, another linear dependence, blue curve, but they're different. So what is the conclusion? The conclusion is that in fact, epidemic progression does not correspond to the usual epidemiological models like SIR, but what we observe here, we observe the acceleration of epidemic progression. So the question which we ask is why this acceleration occurs. So, and we use these immunoepidemiological models to try to answer this question. And since my time is close to be finished, I will not discuss this immunological part of the model. It's, well, of course, it is here shown in a very simplified way, this model, but still, I will not discuss it here. Just I will mention that disease progression for an infected individual depends on the initial viral load. This is very important, and this can be analyzed with these immunological models. So when the initial viral load is low, the individual has more chances to recover. When the initial virus load is high, so the disease progression goes this way to persistence, to chronic infection, or to the patient death. So, and this depends on this initial condition, on this initial viral load. This is very important. And then now we can bring everything together. So why, in fact, we have this over exponential growth in this epidemic development? Because at the first stage of epidemic growth, the epidemic spreads only among people with weak immune response. But after a certain level, when there are already many infected individuals, then the initial viral load increases. And then in this case, infection concerns not only individuals with weak immune response, but also with strong immune response. And from this point of view, the number of susceptible individuals increases. And this is why we can have this transition with from the slow epidemic progression to the rapid epidemic progression, this another exponential. So this is the main idea of what we do with these immunoepidemiological models and heterogeneity with respect to the individual immune response. So to conclude, structure of a heterogeneous population is an important factor which determines epidemic progression. And as we discussed before, basic reproduction number is not sufficient to describe the epidemic progression. So vaccination, we can expect it will more or less soon terminate the acute phase of epidemic. What we can see here, again, these are data for several countries. For Israel, for example, we see that the number of daily infected is almost zero. In the United States, it's not yet zero, but rapidly decreasing. In the UK, it's also rapidly decreased. But strangely enough, it does not decrease yet, for example, in some countries like in Chile. And these numbers here show the proportion of the vaccinated individuals with respect to 200. So it is more or less 200 is because there are two vaccinations, two doses. It's more or less the same in the UK, in the United States, and in Chile, but the results are different. So maybe it's too early yet to say that vaccination stops the epidemic. Maybe not yet. So we should be cautious about that. So to conclude, we can expect, however, that vaccination will terminate more or less soon they could face it at epidemic, but we should be aware about possible long and chronic stage of epidemic, which can be expected after that. So I stop on that. Thank you very much for your attention.
Okay, thank you very much, Professor Volpert, for your very interesting presentation. And now, are there any comment or question or?
I have a question.
Okay.
Professor Volpert, very, very interesting your presentation. Very.
Thank you very much. Thank you very much.
Yes, yes, yes. And at first, I would like to request you, if it's possible, to send me your presentation.
Yes, of course, I will do. I will do it. Yes.
Okay, okay. And is the conclusion that the epidemic progression and final size of the epidemic strongly depends on the heterogeneity of the population is very important. This is intuitively this is very clear. The mathematical answer that you give to this question is very impressive, very nice. I have a question. Which is the difference between considering the heterogeneity of population and considering the variability in time of the rate of infection in the population? Because you can explain the variability of the cases, of the data, using also the temporal variability of the coefficients, which is the
Yes.
difference in general of this.
Yes, of course. What we see in the data, that all these epidemiological curves, and I also showed some data, they change in time, and they don't correspond to what we expect from the epidemiological models. Why it is so? Because due to the measures of social distancing, lockdown, these coefficients of disease transmission, they change in time. So this is why we have these curves which are completely different in comparison with this classical epidemiological models. And in fact, this makes them the difficulty of prediction. Why we cannot predict what will happen later in some country, because we don't know how what measures of social distancing will be imposed and whether people will respect these measures. This is the main uncertainty and the main difficulty of prediction of this, for this, how we can use these epidemiological models in our practice. So from my point of view, and this is what I tried to show in this lecture, is that if we take complex epidemiological models with many different subclasses, there are many unknown parameters, and in fact, this prediction becomes really impossible. If we have only two different subclasses, then we have only one control parameter. It's proportion, the proportion between different classes. And then, of course, well, we don't have an analytical answer for the value of this parameter in each particular situation. For example, the government introduces some measures of social distancing. Of course, we don't know in advance what will be the value of this parameter. However, after some time, with some previous experience, we can already estimate in some range the value of this coefficient. For example, whether the restaurants are open or closed, whether universities are open or closed. We have already this experience. We can have some estimations for this parameter, and we can predict how this time-dependent curve, how it will change due to some measures of social distancing. So you see, it's at the same time, to answer your question, it's at the same time heterogeneous population and time-dependent coefficient, and they come together, and of course not completely, but at least partially, they can allow us to predict the evolution of epidemic.
Okay, thank you.
Also, we would like to give a brief comment, and there, in epidemiology there are always two horizons, we could say. One is to reduce the power of the epidemic in the acute phase, how do you say? Well, the maximum case number, maximum number of cases, and two, the final size of the epidemic in order to finish with it or not, or reach a. And there are a kind of balance in if you analyze the conclusions of your analysis in different points of your presentation, you have kind of balance of these two goals. No?
Well, in fact, we did not ask exactly this question, how to act either on the final size of epidemic or on the maximal number of infected. In fact, we considered them together. We did not consider them separately. We considered them together, and we saw how both of them depend on the structure of the population, for example, or on the vaccination. So we saw, for example, how vaccination of some particular classes, one of these two classes, how this vaccination, for example, acts on the maximal number of infected individuals or on the final size of epidemic. But I agree with you, we can also think about this question in our future works, whether we can consider these two very important parameters independently and maybe act on just one of them. Thank you for this suggestion.
Okay.
So, are there any more comment or question? Okay, so I think we can finish here, and thank you very much again, Professor Volpert, for speak today for us. Thank you very much.
Well, thank you very much for the invitation. It was really a pleasure for me to give a talk here, and I wish good luck for your conferences and for this book with different chapters. Thank you very much.
Thank you very much.
Bye.
Goodbye.
Bye.
Thank you. Bye.